Some years ago, at the National Institute for Medical Research in London, we became interested in the effects of chemical and physical agents on the germ cells. In the course of time, we concentrated our work on the effect of very low temperature, and it led to the discovery that glycerol has the remarkable property of protecting spermatozoa from the fatal effect of freezing and thawing. Our discovery has now been applied to other living material, but the most important practical application so far relates to the preservation of bull semen. Artificial insemination is now widely used in cattle breeding, and it greatly increases the potentiality of a single bull. Nevertheless, under the routine of the ordinary insemination centre, there is still much waste of valuable semen. The waste is due to the fact that by present methods it is possible to conserve the semen in vitro for only about 1 week. Of the factors which influence the survival of spermatozoa in vitro, temperature is by far the most important. Within limits, the lower the temperature the better, because the activity of the cell is decreased and aging is retarded. Until recently, however, the application of this principle had been limited by the fact that freezing the semen was fatal to the spermatozoa. It is here that the discovery of the property of glycerol has been valuable, and by using it we have been able to protect bull spermatozoa from the adverse effect of freezing and thawing, and to preserve them for long periods at the very low temperature of solid carbon dioxide. The method and results of this new technique will now be illustrated, and the detail will be given by my colleague, Mr. Polge, who has been mainly responsible for this application of our low temperature research.
We will first show you an experiment which demonstrates the freezing and thawing of bull semen under the microscope. This is one of the bulls with which a number of our first experiments on freezing semen was carried out. And here, an ejaculate of semen, soon after it has been collected, is brought into the laboratory. A specially designed slide has been made from perspex so that we can watch the process of freezing and thawing under the microscope. This freezing slide is fitted with copper conducting arms, and the preparation of semen is cooled by immersing the conducting arms into liquid air, which is contained in vacuum flasks. We will first demonstrate what happens if semen is frozen in the absence of glycerol. Here, the semen in normal yolk citrate buffer is being cooled. As it cools, the spermatozoa gradually slow down in activity. Now, by the time the temperature has fallen below 10, their movements have become more and more sluggish. At 0, all activity ceases. Soon you will see ice crystals when the semen begins to freeze. There's a slight drift as ice starts to form just outside the part at which we are looking, and here come the crystals in irregular sheets spreading across the field. As the temperature continues to fall, the whole microscopic field now presents a picture of a solid mass of ice. To thaw the preparation out, flasks containing liquid air are removed and replaced by similar flasks containing hot water. The semen here has been frozen to a temperature of about -40 and is now being warmed up. The temperature is rising steadily, and very soon you will see the ice beginning to thaw. There, now the crystals are just starting to open up. Their outlines very gradually fade away as more and more of the ice melts. At 0, all the ice has gone, but you will notice that no spermatozoa start to move. There is no activity even as the temperature rises, and the spermatozoa have all been killed by freezing and thawing. By contrast, we will now show you what happens when semen is frozen in the presence of glycerol. Here it is in 10% glycerol. It is being cooled, but you can see that the glycerol has not diminished the motility of the spermatozoa. The activity gradually slows down as the temperature falls, and at 0, all the spermatozoa are immotile. The ice crystals, which form under these conditions, nearly always assume a feathery shape. Here they come now, on the left, frond-like crystals, creeping across the field. The preparation is now frozen up, but you will see that here, in the presence of glycerol, it looks as if there are larger spaces between the crystals. These spaces contain concentrated glycerol, which does not crystallize. The ice crystals gradually melt away as the preparation is being thawed. And here they have all vanished. As the temperature rises above 0, the spermatozoa very gradually begin to resume movement. You can just see them there, starting to get active. As the temperature rises above 10, more and more spermatozoa seem to be coming back to life, and by degrees the activity increases. Here, at 20, although you can see a certain number of spermatozoa have been killed by freezing and thawing, considerably more than half have survived, and these look just as active as before they were frozen. This is the technique of preparing and freezing semen for artificial insemination. First, yolk citrate buffer, which is kept in a warm water bath at about 30 degrees centigrade, is added to semen soon after it has been collected. In this case, the semen is being diluted with an equal volume of buffer, and it is gently mixed together. Now it is examined for motility after this first dilution. A drop of semen is placed on a slide on the warm stage of a microscope, and a cover glass is gently let down on top. Here you will see the semen showing normal motility. Most of the spermatozoa are very highly active. The tube of diluted semen is now corked up and transferred to a refrigerator. The refrigerator is running at a temperature between 2 and 5 degrees centigrade. It is left here to cool down for 6 hours. After this time, the semen is further diluted with an equal volume of citrate buffer containing 20% glycerol. It is important that this second dilution should be made with medium at the same temperature as the semen. The 20% glycerol citrate is therefore kept in the refrigerator and added to the semen at +2. It is mixed gently by inverting the tube several times. The semen now contains 10% glycerol. The semen is left to equilibrate with the glycerol for about 18 hours in the refrigerator. This ensures that the glycerol penetrates right into the spermatozoa. following day, therefore, it is removed from the refrigerator and the tube placed in a water bath containing ice, so that the semen does not warm up to room temperature during further manipulation. A drop of semen is again examined for motility after it has equilibrated with the glycerol. And here you can see the spermatozoa showing normal activity. Now the semen is put into ampoules for freezing. Glass test tubes, 5 inches long and about 1 centimetre in diameter, make quite convenient ampoules. 1 milliliter portions of the semen are transferred to each tube, and the tubes themselves are also standing in a rack in a nice water bath so that the semen is kept cool. The ampoules are sealed off in a gas flame. This special ampoule sealer has a very hot burner at either side of the tube. They are now ready for freezing. This diagram illustrates a simple piece of apparatus designed to give the correct rate of freezing for ampoules of bull semen. The optimum rate of cooling is at about 1 degree per minute between 0 and -15, and rather faster thereafter. It is made from a 1 litre plastic beaker, which is filled with a quantity of 20% glycerol solution. Into this solution is inserted a metal can containing alcohol. The 20% glycerol solution acts purely as an insulating layer between the walls of the beaker and the metal can. The ampoules of semen to be frozen are placed inside the metal can, and the whole apparatus is suspended in a freezing bath of alcohol and solid carbon dioxide at -79 degrees centigrade. Now, the water in the insulating layer begins to freeze out, and this causes the temperature in the metal can to fall rather slowly during the first stages of cooling to -15. At this point, most of the water in the insulating layer has frozen, and the temperature falls more rapidly. Here is the slow cooler. It has been kept in the refrigerator so that when the ampoules of semen are put into the inner metal container, they are still at 2 degrees centigrade. Now the alcohol in the freezing bath, which is a large vacuum jar, is cooled by the addition of lumps of solid CO2. The slow cooler is suspended in the bath, and the alcohol is kept moving with a stirrer. The temperature of the freezing bath is registering -79 degrees centigrade, and the rate at which the semen is cooled is shown by this graph. The temperature falls slowly to -15 when the supercooled semen freezes out, as shown by that jump in the curve. After this, it cools more rapidly. When the slow cooler has been in the freezing bath for 45 minutes, the temperature of the semen is -70, and the cooler is removed. The ampoules of frozen semen are now transferred to a storage cabinet. This cabinet is made from an open-topped galvanized iron tank, insulated on all sides by 6 inches of expanded ebonite. The air temperature in the cabinet is kept at about -70 by blocks of solid CO2 placed in the metal tank. The ampoules of frozen semen are transferred to a wire basket kept in a vacuum flask containing alcohol at -79 degrees centigrade. The flask is now put back into the storage cabinet, and the lid is closed. Time passes. In this instance, the semen is being kept frozen for 7 months. Now, the storage cabinet is opened again, The vacuum flask is removed and an ampoule of semen taken out of the wire basket and put into warm water. It takes a minute or so for the semen to thaw out in the water at plus 40 degrees centigrade. The ampoule is then removed and dried and filed open. Here we will examine the activity of semen which has been stored for 7 months. We've been unable to detect any great deterioration in the motility of spermatozoa kept frozen for even longer periods. Here is the Artificial Insemination Centre at Cambridge, where, with my colleague Mr. Rosen, we made the first successful experiments on the fertilizing capacity of frozen bull semen. Here is a storage cabinet of a slightly different design. The insulated door opens at the front, and trays in the central portion contain alcohol cooled with solid CO2. The trays make it easier to find the ampoules of frozen semen, and these, as you see here, are transferred to a small field box, which also contains flasks holding alcohol and solid CO2. Now, having taken a large enough supply of semen for a day's work, the inseminator sets off on his journey. He arrives at a local farm and brings his insemination kit into the cowshed. The use of frozen semen makes it possible for the farmer to choose which bull he would like. Here, in the flask on our left, is the frozen semen, and an ampoule is transferred to the flask on our right, which contains hot water. The semen is left for a minute or two to thaw out, while the inseminator gets himself ready for the job. Here, a pipette is fitted with a syringe. The ampoule is removed from the warm water, dried, and filed open, and the thawed semen drawn up into the pipette. While the farmer steadies the cow, the inseminator inserts his arm into the cow's rectum. Through the walls of the rectum, he is able to feel the cervix, and he guides the pipette through the cervix and inseminates the semen directly into the lower part of the uterus. Here is one of the cows on this same farm which has been inseminated with frozen semen. The semen was kept frozen for 5 months, and this cow is pregnant. And here you will see the first calf which was born from semen that had been frozen by this technique. You can see that this calf is perfectly normal and quite strong and healthy. It is just one of the many calves which have now been born from frozen semen, and it is undoubtedly the forerunner of many more which will be bred in this way in the future.